I know there's still one or two people, but maybe we should start. So we're delighted to host Henric Krawczynski, long-standing leader in the fields of gamma ray and X-ray astronomy, and one of the pioneers of X-ray polarimetry, a field which has been a great potential interest for so long, and finally is really seeing fruition. You're the science team with IXPE, as I understand. Also, as we'll hear, the PI of a balloon experiment measuring X-ray polarization and yet higher energy. So is that still unique? I mean, so Professor Krawczynski has been on faculty of Washington University St. Louis for the last 23 years and has managed to become chair of this department for a period of time. And originally got his PhD in Germany and postdoc at Max Planck. So without further ado, welcome to Toronto.
Thanks for welcoming me for the short notice seminar. Really nice here. I want to stay here all the time. So many specialists.
You're welcome.
This is awesome. Yeah, so I want to talk about X-ray polarimetry, particularly IXPE, which had the satellite-borne experiment was launched in 2021 and has had a great run with great results. Bit about XL-Calibur, which is the balloon-borne experiment at higher energies. A lot of the results I have are about Cygnus X1 just because it's kind of the widest, so we can study it in great detail with short observations. And it's well constrained in all other, like with many ways, different wavelengths. So as you know, light beam is completely characterized by the intensity and then by the 3 Stokes parameters. And 2 of them, Q and U, give the linear polarization and V the circular polarization. So X-ray astronomy for between the late 60s and up to 3 years ago were mostly about the intensity, measuring as a function of energy and time, but now it's also possible to measure the linear polarization, the Q and U Stokes factors, which give polarization about 2x, 45 degrees. Circular polarization is still super difficult. You have to scatter off polarized, strongly magnetized iron foil or so. It's super small efficiency, so that's kind of, it's not possible for anything we know right now. Why is it interesting? You can study X-ray by compact objects and infer about the magnetic fields and the scattering geometries. Why is it difficult? Because you need a lot of photons. You need 10 to 6 photons. And usually in X-ray astronomy, we don't have that many photons. So Chandra detects the source often with 5 photons. And with 100 photons, you get a good energy spectrum. But to measure 1% polarization degrees, which are kind of the order of magnitude you see from black holes, you need like 1 billion photons. So you need a lot of photons, and that's why it's difficult. And very high efficiency broadband detectors. So the 2 polarimeters, one is this mission IXPE. Martin Weisskopf had been the PI initially, now it's Phil Carré. And the instruments, the polarimeter, come from the Italian collaborators, from Paolo Sofita. And so it measures from 2 to 8 keV and measures a few percent polarization for a millicrab source, was launched in 2021. The photons kind of go into some proportion in some gas chamber where they knock out a photoelectron and that flies into the direction of the electric field. So if you measure the tracks of these photoelectrons, you can infer the polarization degree and direction. I've been working on this XL-Calibur, so it's a 12-meter long telescope, and it uses scattering polarimeter. So that it's usually in space, it could work starting at 4 keV, but on a balloon it works above 15 keV because the atmosphere absorbs anything below 15 keV. Then it's really a nice process, has high efficiency, good modulation factor with Compton scattering. The Compton scattered photons basically, they scatter perpendicular to the electric field direction. And if you sample the scattering directions for 10,000 of photons, you get the polarization. There's also lower energy, which is super interesting, for example, for the thermal emission of magnetars, which could be super highly polarized. That will be possible with red socks or ghost socks with Herman Marshall at MIT has been working on, where he kind of fans the light out with a multi-layer grading, with a grading, and then with a multi-layer films reflects it and measures polarization. So that could be work below 1 kV, would be super interesting. And then above our energy range, the next mission will be COSI, which hopefully will be launched in 2027. And that kind of measures to 5 MeV, and because there's Compton scattering is also polarization sensitive. We're pretty optimistic that it will be launched. On the top of that, the Italian team is preparing an ESA M8, very ambitious follow-up mission to IXPE, which goes all the way to 40 kV, or 80 kV, by Paolo Sofita. We have been thinking of submitting SMAX or MIDEX missions proposals just for hard X-rays. This Red Sox will be launched on I think a Pioneers mission in a few years. The GoSox. Let me briefly go about the XL-Calibur. You see here the telescope in Sweden. There's lots of people working with it, so overall we have 50. The main collaborators are from the US. We do the detector, the overall mission design, and group at Wallop Space Facility that's a pointing. So while the thing is dangling on the balloon, we point with a few arc seconds stability and a few arc seconds pointing knowledge. Then the other big groups are one from Japan. They provide a mirror, which is a spare mirror of the Hitomi mission. And it's a 12-meter focal length, large effective area, multi-coded mirror that collects the X-rays and focuses on the detector. And then we have Swedish collaborators, and they make the anti-coincidence shield, which is super important for these high energies. Here, this is a mirror, platinum carbon coated. We have like a star tracker. This kind of gives localization every 2 seconds for star images. And then 100 times a second, we get an immersion flight unit to stabilize the point.
Main background of these entities is cosmic rays.
It's largely, so a lot of background is from cosmic rays, the atmospheric gamma rays that are produced from cosmic rays in the atmosphere. And then there are also the primary cosmic rays. And that's a pretty hard background, and we have like 6 centimeter shielding with heavy BGO crystals to shield it out actively with a light flash and then attack events, which are background events. This is a mirror, 213 shells, platinum carbon coating. Each mirror has like about 80 layers or so. So it's a really advanced thing. This is our polarimeter, so we use a beryllium stick to scatter the X-rays, and then we have cadmium zinc telluride detectors to detect them and measure the energy. So it also gets good energy resolution and timing resolution. There's a developed that at WashU, and it uses some ASICs from Naval Research Laboratory. This is the active shield into which the polarimeter is lowered, and then we have PMTs, which give us electrical signal when cosmic ray strikes, which may then produce secondary particles which hit the detector inside. And everything rotates to minimize systematics 2 times a minute. We have this at WashU built like a 12-meter carbon fiber truss and focus the X-rays on the polarimeter. This pointing system, which has like motors which run all the time and counterclockwise, so to have no static friction. Very complicated telemetry with all kinds of different satellites or channels. We flew first really successful flight in July, on July 9th from Sweden. You fly it from the very north or from the very southern hemisphere, where in the spring you set up a circumpolar vortex. And so if you launch a little balloon, you pretty much know where it's going. And they have like an uncertainty of where will they land, but it's kind of, they will land over Canada. If we had better relations with Russia, we could go around many times, but now we have to stop after 5 days, 6 days. And this
Greenland is still okay.
You would say it's still okay. In the southern hemisphere, you can go around many times, and so if you go around 8 times, you can fly 55 days or so. That's much nicer. We want to fly from there, but there's like a backup of missions because of COVID. So we spent 4 days, 16 hours, 51 minutes. This is just shows its function of energy between like 15 and 60 kV. The red one are all counts, the black one are background, and then the blue one is our excess count. So that's a crap energy spectrum. Just it's probably one of the nicest energy spectrum taken from a balloon. We have like 60 or 80,000 photons. And then this is a polarization signal. So we measure something like 24.7 plus minus 3%. That is for the phase integrated. Phase resolved is very difficult, and we basically only have upper limits. But that's the best measurement for polarization. If you compare to what IXPE measured, IXPE is kind of a bit off relative to the jet that you see in X-rays. Our signal is very much aligned with the jet or with the inner torus of the Crab nebula. Like at higher energies, the Crab nebula is smaller, only the torus emits basically. You get less emission from the outer regions, which kind of seem to move the X-ray polarization around. But ours is very much aligned with our result here, with the direction of the jet. So that's kind of what I wanted to, this just shows that different energies, how the Crab nebula gets smaller. That's from new star. So it gets smaller as you go up to higher energies just because the electrons cool radiatively as they move away. Let me switch to the main topic, which are binary black hole X-ray binaries. And I will talk about these two states. So they go into two states. Actually, not clear which one is a wild one or which one is the honor one. But one is the soft thermal state and one is a hard state. Soft thermal, we think we know more or less what's happening. We should have this Shakura signal pretty much this, pretty ordered. We hope to be able to, or we set some limits on black hole spins, inclinations, maybe check a bit of strong gravity, but realistically speaking, the astrophysical uncertainties are always much bigger. For the hard state, it's then more about just a kind of constraining black hole accretion and understand how the hard state works. So the luminosity is a few percent adding luminosity typically for these objects. Yeah.
Sorry, I asked a question on the last slide. Can you say a little bit more what kind of emission is for the soft state and the hard state? I guess the soft state is like the disk, and then the hard state is, I don't know. There's a lot of thinking there.
Right, so the soft state is super interesting. Basically, you get this multi-temperature blackbody emission, which is then kind of modified owing because it goes through the atmosphere of the accretion disk. And in higher altitudes, the temperature increases a bit, so you get a diluted blackbody emission, which still is very much blackbody, but for the area, it shifted to higher frequencies. And I'll show you that maybe that's not fully true, because you see stronger polarization than you think, and the polarization direction doesn't agree with what this would predict. Because maybe you know, when scatter, you always polarize perpendicular to the scattering direction. So if I come up here and scatter to you, it should be polarized in this direction. So it should be polarized parallel to the disk. But it turns out, signal X1, it's parallel to the jet and perpendicular to the disk. So this simple model that is just blackbody reprocessed in a static atmosphere does not work, actually. So the soft state is more complicated, already gave away one of the main results. Here the hard state, and Bart can confirm that, very much unknown exactly what's happening. If it's like a disk that someone truncates and you have just a hot inner flow, or these are some region between the jet and the disk, or some patches of hot gas which bubble up in the disk, so nobody knows. But somehow gas gets compromised. And the seed photons are likely from some disk, but maybe the disk is integrated mostly, and then maybe the seed photons that are compromised are maybe Bremsstrahlung and all kinds of different emissions. But I think the main conclusion for the hard state is that we still know very little actually about the properties. So they accrete at a few percent adding, like in stationary, I'll show you a bit later. Cygnus X1 accretes at 0.5% in the hard state and 1% or 2% in the soft state. In flares, it's like 10 times more. So you get polarization by reflecting, and then it reflects perpendicular to the scattering plane, just because the dipoles kind of be in the direction of the reflected beam. They don't emit in that direction, and therefore gets polarized perpendicular to the scattering plane. This can, if you have a homogeneous atmosphere, can polarize up to 11.7%. This is what we call the Chandler-Zecker polarization. From single scattering, multiple scattering, if you add up all orders, you get 11.7%. That's actually very constraining because some objects are as strongly polarized. And usually you would think that's an upper limit. And then, for example, we add the fact that X-rays orbit the black hole and get reflected, and that has a different reflection direction, and then you get a then smaller polarization. So that's actually kind of really interesting that this that some objects are close to this maximum. Faraday rotation, I used to say it's negligible, but actually now I think it's really interesting. There may be some Faraday rotation happening, and they may just depolarize because different region, different types of Faraday rotation, they depolarize. So we can actually get some limits on the magnetic field structure from the fact that we see strong polarization. And then as an X-ray propagates and goes, for example, around the black hole, the polarization vector always stays perpendicular, so it kind of moves along and is parallel transported. And therefore, a photon which goes around the black hole and then comes to us, or reflects off the disk, it counts different in polarization than in the energy spectrum, because the polarization kind of changes as it moves around. It's dependent on the path. And some people call that gravitational Faraday rotation. But it's an interesting effect, and that gives us some sensitivity to where the emission comes from. And it comes very close to the black hole, it goes around, it changes. So the big picture, and you know that better than I do, you have accrete mass with some accretion rate, some magnetic flux. You have the differential rotation of the magnetized plasma in curved space-time. You get turbulence, creates B field, and the B field, so that's kind of a mechanism which amplifies, which kind of provides some of the angular momentum. And then you get angular momentum and mass transport. Then turbulence, shocks, and reconnection transfer some of that energy and into energetic electrons and ions, and they give the emission. The red thing is kind of the thing which is really exciting because people are still studying this and with simulations and observations. So, for example, general relativistic radiation, magnetic hydrodynamics, or pick for the turbulence shocks and reconnection. This is like an overview, and this is from Mayumda et al. There's a nice paper where it shows all the black hole X-ray binaries observed with IXPE a few months ago. It shows the polarization degree, which is typically between 3 and 7%, as a fraction of the disk to Compton ratio. So if that ratio is small, we are kind of basically in the hard state. If it's high, we are in the soft state. And you see in the hard state, we have higher polarization than in the low state, kind of goes down. So the hard state here on the left-hand side, these kind of results. You learn about accretion from plasma physics, soft state, black hole spins, inclination, strong gravity. If you look at this, there's lots of information. There's some outliers. These what are they called? Diamond shapes. They're the surface X3, which we think is actually not a black hole, but an ultra-luminous X-ray source, which is obscured, and then the reflection of the obscuring gas gives probably this very high polarization for up to 20%. So that's a Cygnus X3. Another outlier is this one here, is 4U 1630s minus 47. This is also super highly polarized in the high soft state and in the soft power law state. So not fully clear what is going on. A high soft state is kind of, it looks like a perfectly thermal spectrum and is super highly polarized. The polarization direction didn't change between these observations. Then you have, for example, Cygnus X1 here. I show you more results in the circles, and it gets a bit less polarized in the high soft state here.
So the more you go to the left, the more order the magnetic field will be. So reasonable to say?
Right. So in the old times, we thought this would be true, and this would be kind of less polarized because you just get the emission from going out of the accretion disk atmosphere. And here it's more polarized because you get the the reflection in the corona with a fixed geometry.
Or if the X-rays are going up, then they get scattered to the side. That's a good way of producing polarization.
Yeah.
So
And then if the corona is kind of flat, then even you get a lot of these scatterings in the same direction.
If the corona is more compact vertically, then it cancels out.
And all of the ones on the left in the blue band, do they have jets?
So
Radio jets?
Cygnus X1 has, and GS 339-4 has, which is it here. The other ones, I'm not sure. They're probably in the hard state. They do have jets, but what is it trying? Swift. This one, oh yeah, has a beautiful jet too. And for all the ones in the hard jet, actually, it's always aligned to get the polarization.
Yeah.
So the three objects in the hard state, it's aligned with this IGR, this one here, I'm not sure if that has a jet. Maybe it's just has not yet been imaged, but I'm not fully sure for that one. But for Cygnus X1 and GS 239-4, it's parallel. And for the J1727, that has an image jet and also is parallel. These are the three, I think. For this one, I'm pretty sure. So the baseline model, which I call the standard model, or the baseline model, the soft state is a submission from geometrically thin object disk, dominates the polarization. The polarization angle should be parallel to the disk, electric field polarization angle. Hard state, you have continuization of the disk emission and the laterally extended corona. That dominates the polarization, and the angle should be perpendicular to the disk. These are all the objects that have been observed, I think 13 or so. And so the green ones, they agree with the standard picture. For example, LMC X3 has a polarization of 3.2%, which is consistent with a low spin and sets some limits on the spin or inclination. The red one are the kind of interesting one because something unexpected. For example, first, the hard state polarization is harder than you would expect for the low inclination. And in the soft state, the polarization is parallel to the jet. And I will show you that a bit more in detail. So the red ones are kind of surprising. All of them have very high polarization. And we have this funny that the polarization direction doesn't seem to swing, which was kind of predicted. So that's kind of the exciting stuff, in addition to Cygnus X3 being a different object quality, because it is just off the charts in terms of polarization. Cygnus X1, so I want to focus a bit because parameters are well determined. Black hole mass, 21 solar masses, companion 41, period 5.6 days, inclination 27.5 degrees. Kind of interesting, there's like a new paper with UV observation. They have a second minimum for a higher inclination, and the mass that they determined varies strongly with inclination. So maybe we should just be careful that these parameters may be not that fixed as someone sometimes thinks. Just for Cygnus X1, you see that it's sometimes, these are like 500 days each, overall like 2,000 days. It stays, this kind of shows the flux and this hardness ratio. It stays sometimes very long in the hard state and then goes in the soft state. It's kind of amazing how long it's stable sometimes. Probably something happens with how matter is accreted. So over 4 years, kind of surprising.
So if you make a switch, I don't know if it's actually visible. So Krawczynski has been working on naturally producing loops with alternating polarity. So if like one loop creates with certain polarity, you shoot out a jet which is in that direction, and then it switches off, so it goes to soft state, and then you create an alternate polarity loop, and the jet in our oscillation sense goes has the other orientation. Is that something that could be distinguished?
So which time scale does it go up and down? Because we observe always like 100 kiloseconds or so, and I don't know how fast it switches up and down. The dynamic time scale is like 0.9 millisecond.
Is your question, anyway, the sign of that?
No, I know we cannot. That was great. But are you simulating the right time scales? Because you could see.
Not energy issue, like probably would be order of seconds, I guess.
So we'll explain that later. I think some of the stuff has to move to explain the hyperpolarization. If that moves to us and from us, that would be a big difference.
Yeah.
So that would kind of give a mark. It was basically seeing it at very different inclinations or so. So if that happened, you would see, I think, a big change in flux and polarization.
Yeah.
If it's really beamed. So if we look at limits, observation on the size of the emission region from time variability, maybe there's a little bit of relativistic motion. Then for the soft state, 7 millisecond flares are observed, which is something like 34 Rg. Or on the hard state, it varies on slower time scale, so it could be even actually 130 Rg. So for the hard state, we don't have that good limits on the size. There are some limits from time lags, which says something like 72 Rg, or from lamppost modeling, which by now we think actually is not accurate because it wouldn't explain the polarization right. That gives like something between 20 and 40 Rg. So that's kind of the limit on the hard state coronal emission region. Something between like on the order of 130 Rg, maybe smaller. For the soft state, a lot of emission comes very close to that point. The spectrum here, soft state, has always this power law. That was something we discussed before. That was actually interesting. Some of that comes from either still comptonization, maybe by bike plasma, or maybe something is a remnant from the initial reconnection and particles accelerator. In the hard state, you have this comptonization dominating up to like 500 kV or so, or 200. It kind of starts to cut off at 200 kV. And then there may be additional like harder components.
And the dashed line is correct before, so.
Yeah. So that's actually interesting that the time average is not that different. 2% if you take this into account, and 0.5 in the hard state. For flaring state seems to be very similar according to this analysis, was correcting for the energy at low frequencies. That's from actually missing the reference. Does it come still? That's from Krawczynski, 2002. It's in a really nice paper. Accidentally deleted. Oh, no, here, it moved over. Oh, this also applies. Krawczynski, Krawczynski.
When you measure the polarization, you have to integrate for a very long time, right? How do you get Stokes eyes hardness ratios at box so you always know which state you were in during the integration time? Pretty much.
Because it doesn't go so quickly from one state to the next. So usually it stays for a few weeks or so. Just wanted to show you there's some model of the wind from Cygnus X1, which has been normalized to the phase-dependent X-ray absorption. So you're only sensitive to the neutral hydrogen column density, but you do get some handle on how much accretion, how much mass you accrete, and that would be 3.2 L Eddington over C square. So that's the total energy you have, and then you see 0.5% or 2% of L Eddington coming out in X-rays on average. So that means you need an efficiency of 1% more or less, or 2% conversion of accreted mass to emission. A couple of percent. Depending on how big the corona is, you can kind of make use of this gravitational energy, different amounts of gravitational energy. If the corona is really extended, you can only make use of 2 or 3% of MEC squared. So that's actually extended corona quite difficult to reconcile with the total energy you have at your disposal. It's still okay, but it's kind of borderline. It has to be really efficient. If you kind of, most of the energy extracted between 5 Rg and the ISCO, for example, at 1.2 Rg or so, then you have like 20% of the rest mass energy that you have. So then you can still lose energy by a magnetic field that doesn't radiate, or by kinetic motion that doesn't radiate. So the complex corona is more attractive.
Well, can you comment, what's your opinion about the reliability of black hole spin measurements?
Very low, very low. Yeah, no, that's very low. There's actually a nice study from Krolik and his postdoc, Chris, I forgot his last name. But they kind of have relativistically broadened ion line for matter pretty far away from the black hole. So it's not sensitive to the spin at all. So the black hole measurements don't seem to be reliable. In addition, a lot of the work for the iron alpha line was based on this lamppost, which we don't think is correct. And continuum methods, so kind of what's really suspicious is that you get these 0.998 spins very often. So I have one thing which changes the spin a lot. I'll show you. Just wanted to show you a very nice project we are doing by my postdoc Kun Hu and with Bert van der Meulen. And he models the reflection of the star and the focused wind. And this shows a black hole in X-rays and his modeled X-ray reflection of the star. And if the black hole is behind the star, you don't see much of reflection. If it's front, you see a lot of reflection. So he predicts a signature for how the polarization should change. And it changes by about 1%. So we'll try. Interestingly, it only changes at a higher energies much more than a lower energies, just because more X-rays reflect. So all the analysis which has been published by Krawczynski only looked at all bands, but if you only look at higher energies, you should see that modulation. So that basically also depolarizes a little bit that signal because you get it mixed up. Let me go to the surprising results. So soft state polarization, you see here a nice soft state energy spectrum from the paper of Jack Steiner. Has this little bit of power law there. And then here's the polarization degree and the polarization direction. And you see that the hard state is more polarized with 40%, but the soft state is pretty strongly polarized as well, and the direction doesn't change. Even though it's always parallel to the jet. Even though you think we understand the soft state and it should be perpendicular to the jet, if it just comes from scattering out of the atmosphere. So that tells us that something is not right with the standard model of thin disk emissions. So that's really exciting. Parallel to the radio jet, this shows this other object, 4U1630-47, which is polarized between 5 and 10%. You also see that the polarization is much stronger than by all our standard model, where you get just the polarization from the Chandrasekhar reflection in the disk atmosphere. So it's a factor of 2 or 3 stronger polarization. So we have 3 explanations. The number one is the reflection of gravitational lensed emission. And that's an analysis by postdoc Kun Hu, and we published that in the Steiner paper. So this is just if the black hole is spinning super rapidly with 99.8% of the highest possible value, then a lot of emission comes very close to the black hole, and a lot of emission orbits and reflects, and that reflection ends up to be parallel to the radio jet, that polarization that you get from that reflection. So it uses a lot of fine-tuning, and you have to get the matter really close to the black hole. In that case, you get the right polarization direction through reflection, and you also get the right polarization degree. It's kind of a bit unhappy with this hypothesis because we need this 99, I think it has to be more than 96% of the maximum spin to get this result. Yeah, 96%.
Can you explain a bit more about what is the, how is the reflection working in this work?
So we think close to black hole, plasma is super highly ionized. And so basically you reflect 100% Thomson scattering. The X-rays go around the black hole and then hit the other side of the accretion disk and reflect and come to us. And some of them can reflect many times. It's actually another paper we were writing about, there's something like you actually can get a power law just from multiple reflections. It's kind of cool. Just from general relativistic, you get to a high spin.
Wait, at the reflection, what's happening? The photon coming down to the disk?
It kind of comes side or down, and then it kind of Thomson scatters.
But it's oblique to the disk then, when it's reflecting.
No, they come at all angles, they kind of, because some of them kind of go barely touching, barely make it above the plateau. Some go like pretty wide around.
So this would depend on the inner edge of the seam disk, right?
So basically, in the first 1, 2 RG or so, like a lot of photons go around and come back.
1, 2 RG.
Not fully remember exactly the range, but most of these effects goes away once you go below 0.9 spin. So it's mostly dominated by the very close to the hole. These guys come back.
You can get a lot of gravitational, like all of the photons over there would be circling around quite a bit. And I expect that there would be some cold matter in that region anyway. So there you might go.
So they, up to now in our model, we only consider the reflection of the disk. In addition, there's this plunging region matter. It may still add a little to it. We don't think it changes a lot.
Sorry, I was just giggling.
So that's kind of interesting because it would be strong gravitational lensing if this hypothesis is right. So the other one is that we think that maybe there's a pair wind that moves like this kind of building on Andre's model in 1998 that he had for AGNs for the coronal emission, but maybe that's also happening in soft state, that you get pairs, and then for many reasons they start to fly away. And some of that is because of radiation pressure, but there's also emission pressure. And so kind of the idea is we have magnetic flux accumulates, you have reconnection accelerates particles and the gamma rays and make electron positons. They cool really rapidly on inverse Compton, and then they get accelerated by different effects. And you end up, and if you have like a wind of half of speed of light, you would have a wind pretty low temperature, such as the Compton temperature of the disk, like of a KV or so. It would basically be a cold wind. And the amazing thing is that it changed polarization a lot, but the spectrum almost not at all. So we ran this little simulation for different velocity profiles of this pair wind. And you see here, it depends on the inclination, but for this inclination, for example, the energy spectrum barely changes, depending on the model, but the polarization, instead of being horizontal, goes to parallel, and instead of being only like 2%, it goes to 8% or so. So you can really have a very strong polarization just by this pair outflow. It would also change the spin estimate, because depending on the angle, it can change the spectrum too. So that is kind of maybe that, and that's another paper of Szydiarski for non-moving pair layer, that such a pair layer would change the spin. But that's also for our moving pair layer, it would change the spin estimate from continuum figures. So that's our explanation number 2. Passing X-rays through the half speed of light pair wind doesn't change much the energy spectrum, but changes the PP and the PA. We need to revise. Okay, that was only 2 explanations. These are our only 2 explanations right now. Either a pair wind or extremely high spins. And nobody else came up with another explanation. So for hard state, this was an initial observation we did with IXPE. It was super exciting. And they let me be first author, even though the experiment was built by people. Fabio was co-author, and the doctor, and Alexander Valentina. So you see the radio jet, which is like 10 billion kilometers large, and then on top of it, the X-ray polarization measurement with 3 sigma error regions. And you see it nicely aligns. Actually, the main uncertainty if it aligns or not is because the jet is from period to epoch, you see a little bit different jet direction in the radio. So with an accuracy, it's perfectly aligned, the electric field. And that, if we had a, so this polarization seems to increase a bit with energy from 3 to 6% to 8 kV. That's a follow-up paper from Krawczynski, which shows that the polarization gets larger in the hard state and smaller in the soft state. But the polarization direction doesn't change, which is kind of amazing, because we are pretty certain it should be 90-degree flipped. This is our XL-Calibur result. You see light curve, which just shows like that we have different inclination, atmospheric absorptions. We measure the energy spectrum within a hard state. And then these are our polarization results. So basically we get also something like 6% polarized in the same direction as IXPE. And then if we split it up in energies, at low it's not that significant, it's better at higher energy, 33 to 60 keV. It's kind of consistent with the IXPE results. And the direction is consistent with the jet direction. And if we show as function of energy, so this is IXPE, this XL-Calibur point, and then maybe at higher energies, these are integral and astrosat, maybe gets polarized more. But where we are, it's kind of polarized only to 4 to 8% or something. Our upper limit, I think, is 12%. This could be because the coronal emission kind of tapers off, but these results are not, if you model it, it would go up a bit later. So it will be exciting to measure viscosity and see if these results at higher energies are correct. So maybe that's a jet taking over the polarization. Just show you other hard state sources, which are very highly polarized, 9 to 12%, or 9, kind of about 9%, this IGR source. And then the SWIFT source is also polarized to 4%, I believe. So the hard state exceeds the expectation from the standard picture, and that could be maybe the inclination of the disk is different from that of the binary, or that of the binary hasn't been measured well. Then with 40%, 40-degree inclination, we can explain the results.
So the jet direction is consistent with the black hole beta line, but there's some ambiguity in the jet direction.
Yeah, this would be double odd, basically, because the jet direction, as you say, is aligned, but it would have to be inclined differently. So it would just be in our dimension inclined, but not in the other.
So it's possible, but it requires
but
it's quite fun to do.
Then the second explanation, continuizing corona is outflowing to Bhutan, that's basically the Andrei-Boloborodov model again for corona. And or the relativistic reconnection produce higher polarization than just the standard continuation. That this bulk scattering of plasmoids it gives a higher polarization than just isotopic gas, because the plasmoids are not isotopic. So
in Navin's paper, in essence, the corona is also outflowing. Is that a combination of it?
So we just wanted to show, we did this kind of model, phenomenological model, simple toy model with the disk analytical model and then continuization. And we ray trace X-rays and we allow for all kinds of interaction between disk and corona. We model that for 68,000 configurations with different parameters of the corona. It's all phenomenological kind of, these models are not self-consistent, but we should cover everything basically. But they all have the same temperature and the same optical depth. But then we can kind of really fit the data, and we fit this, and then you get, for example, that you can fit with inclination larger than 45 degree and 60 degree gives a good fit. In the paper, the science paper, we put this plot where you see here's a jet direction, and then you see for different models, for example, lamppost, you see the polarization direction and strength and degree, and you see it's all off. While for the corona being on top, like a sandwiching corona or inner hot flow, you get the right direction. And then you get the right polarization degree for something like 50 degree or so. So if the inclination is different, then we could fit it with a standard model. 45 degree, or depends on the model variable. But so the other thing we have been doing together with Bart and Navin and Lorenzo and Jordi, that we look at the polarization that you get from continuization not of a hot isotopic gas, but by the plasmoids. And John ran this toy model basically that Andrei Boloborodov came up with, where you have like the plasmoids are in the plane of the current sheet, and you scatter off those. So you kind of we've tuned to kind of more or less fit the energy spectrum here. The blue points are the measured energy spectrum. And then the black are different models, which are kind of similar. nicely, you actually do get the swing from the polarization parallel to the jet. You do predict the polarization parallel to the jet. Even though the blobs are all flying in the plane right now. This is a simple toy model, doesn't have any space-time. It's just the polarization of a 2D reconnection sheet. And it produces polarization perpendicular to the sheet. So if this, for example, lies at the center between a truncated disk and the black hole, and it was just a sheet, it would produce the right polarization. And then if you kind of would move it into the jet wall, the polarization would be lower, but it still would be kind of in the right direction. So get high polarization perpendicular to the current sheet. And now we want to look if we can inform this from the results from the resistive geometry. But there's kind of some problem, how do you generalize from these 2 simulations to 3D? But that's kind of interesting thing. So you can gain some, not only assume a simple 2D model, but kind of try to see how that looks in 3D. Wanted to show you a few other more simulation results. Very popular model is this model where the thin disk is truncated and then you have a hot inner flow gas. And my student Zoe simulated that. And the kind of interesting thing is that you always overproduce the thermal emission from the disk. You always produce a gigantic thermal peak that you don't see. And you can say, well, just move this truncation radius out and the temperature will get lower and lower. But we went through the entire parameter space. You cannot do that. You always should see the soft excess. So this truncated disk hot inner flow model doesn't work. You don't get enough seed photons from the outer disk. So you need additional seed photons by, for example, the disk reaching into the corona, or by some other clumps or some emission, synchrotron emission.
Or the mass has to get through.
Right. So.
See, there's a truncated disk simulations by Jim Buckles. She's not here this week, unfortunately, but you see an inner current sheet.
If that's it, yes.
And then the disk is truncated at some radius, but then you see spirals of accreted matter that's relatively cold coming in. I'll show you.
Yeah, so that would do it. You need somehow photons inside. Last thing I wanted to show you. So that's just a kind of paper with the holiday season. I kind of bought in a few days. So if we like magnetically dominated models, then the magnetic field has to be pretty strong. So maybe we should see validate rotation. So maybe I look through the 3 models of how energy could convert it from magnetic field into radiation ultimately. One is this plasma-dominated reconnection where the plasma moves with 0.01 speed of light into the reconnection zone. Then maybe fast reconnection where it moves with 0.1. If you look at the Goodman 2008 paper, the estimates of when you could get fast reconnection, and you just can get it at with an 8 RG or so. It's a bit of a reach, but so this is radius in RG, and this has to be smaller than 1, and it kind of holds up to 8 RG or so. Or you maybe can even faster move some plasma that kind of, for example, is in little knots, and then the knots undo and it relaxes, and then this plasma could just move at the speed of light and then give off its energy. But it's a question, how do we load the plasma to be so tense that it wants to give off all its energy so quickly? But you have different velocities, and to explain the observed luminosity, basically the energy transported in has to equal the radiative energy coming out, taking from all the inefficiencies, and you can balance them. So the slower the plasma moves in, the higher magnetized it has to be if it wants to provide the energy. So if you just say this is the energy density that you infer from observations, and you say that has to move in kind of from a disk between radius r and r1 as the inner radius, but the plasma moves in with the velocity beta disk, like in the dissipation region, and then you have an efficiency of eta watt of converting magnetic field into radiation, and maybe that's a half, because half of it, the magnetic field, half of it ends up in the the pseudomagnetic field, and the other half is converted to radiation. And then you compute the Faraday rotation, and then you look, because you think there's lots of different regions, so you actually don't observe one rotation, but you observe the depolarization. So you kind of average over all of these with this amplitude. You get that the net RMS of the Faraday rotation is 3.74 radian, and then it goes down with E square, with the energy square of the photons. And it depends on how fast the plasma moves in and how efficiently it radiates, and how many independent regions you have with different orientations of the plasma. So it's just, for example, you want to have very ordered magnetic field opposing lines that move in, and the X-ray escaping would have to go through all this ordered magnetic field. You would see very strong Faraday rotation. But if it's all the magnetic field goes in different directions, then the Faraday rotation doesn't add up but cancels partially, and you suppress it with 1 over square root of the regions. But this is actually really, I think it's an interesting constraint. So this shows as function of the RMS of this Faraday rotation how much depolarization you get. And 3.7 is kind of here, so you would have no polarization left even if you start with 100%. So if you want to have only depolarization by a few percent, let's say you want to have this smaller than 0.2, I think it's it. Then this product has to be larger than a certain value, and it's actually 350. You want to end up here, I believe, here, 0.2 again. So these ones are kind of natural values, and so you need quite a lot of regions to come up with a product that's larger than 350. Or you have to have faster moving magnetic field or higher efficiency, but it has to be kind of ordered in some way, the magnetic field, not ordered. So it just is a constraint that you could use and check models if they satisfy this constraint. Basically because we think, basically it's very strongly polarized, so it would be difficult to explain if we had strong Faraday polarization. So to conclude, soft state, maybe we have these pairs that flow out and change the polarization. They would explain the stiffness X1, strong polarization, from which we haven't seen phase dependence yet. So we don't think there's much reflection going on or so. For the hard state, you also have probably some outflow in plasma to explain why we can see up to 10% polarization degree. That may be like the foot or the base of a jet, which kind of powers a jet, or may powering a wind or something. So I'm kind of interested. Pairs is already in PIC simulations, but only beginning to be so. And it's really difficult to get pair loading in GRMHD models. But maybe the observations depend a lot on these pairs. So that's kind of, okay. So I'm really fascinated with the pairs right now because they come up here. To summarize, we have these nice observatories, IXPE, Calibur, and then they come together with numerical simulation, GRMHD, different variants, PIC and GRPIC, and then together we get like new insights about black hole accretion. And so it's a nice time for this kind of physics for the next decade or so, I think.
Thank you very much. Further questions? Can I ask you, what's your opinion about the arts-off delays? The extent to which they really are geometrical in origin?
So I have done little analysis, and it always depended very much on the cuts you use. So I think I'm not fully qualified to. But the thing I did seemed it's not super robust.
It's just these low luminosities. You go out to 50 RG. It's hard to get things to collide with each other. And if you make pairs, say, and they flow out, well, then they become more and more transparent. So the natural place to have a lot of the scattering is, around the ISCO or inside the ISCO.
So when we analyzed our X-ray data, then it depended a lot on which bands you used and which frequency filters you used.
Questions?
Does the polarization measurement depend on the sample mass of the black hole, or type of companion stars there is?
Yeah, it should. So for our black holes, actually don't know if we have enough information to make a scalar plot. We haven't made a scalar plot. It's a great idea to do this. But so Cygnus X1, it's good to make a plot. It's a nice idea to plot the parameters again, black hole mass or companion mass or orbital characteristics or so. Yeah, that would be interesting.
Yeah, I was just wondering because initially you mentioned there are 3 systems that are very different from the rest, and then I was thinking, oh, are they high mass X-ray binaries or low mass X-ray binaries, like where they are? So.
Right. So for Cygnus X1, we think we know the black hole mass and the companion mass. For the other objects, we often know very little. For example, for you, the mass estimates range between 10 and 80 solar masses, and people don't know the distance. So a lot of these systems are not well constrained. But it's still worthwhile looking, and I don't think anybody's done it.
More questions?
Appreciate it.
So for Cygnus X1 in the hard state, are there reflections? Like, is there any reflection?
Yeah.
Okay. So
And we tried that was actually one of my main motivations to do this very lengthy modeling. I'll show you. So we simulated the 68,000 configurations, and for each 20 million geodesics. So overall, we had it's actually wrong. We had not a billion, 1 trillion geodesics, which we all store on disk. And then, while fitting the data, we dress this up with the silver reflection for the plasma, self-consistently calculating the ionization of the gas. And we tried to fit the iron alpha line, and we never managed. All this detailed modeling with the reflection, the lines which are too weak and too poor. Weak and rather poor. Like they didn't show up when I never managed to fit the actual data. But in the lamppost model, you fit it and you get a pretty high spin, inclinations of some fit with 27 degrees, some people fit with 45 or so. So the lamppost model, people have done that a lot, and you often get these super high iron abundances, which you can suppress a little bit. But
so in the lamppost model, is the constant on the edge of the disk also like IXPE?
Yeah.
Okay, so they need the disk to be very close, I guess.
So the constraint on the spin is something like 99.
Yeah, so it has to be very.
The corona that I had the number there was between 19 and 35 RT, the corona height in the lamppost model. That was the latest model from Tom Sickett with the high density model of USC.
Because like in some of these radiation GRN simulations, other than the spirals of the geometries, you also get some clumpy material sometimes. And these are cold as well, like really cold. So one question was that if you had some clumpy materials, would that explain one thing, whether that you get a reflection spectra, and whether that would help with the polarization as well?
So what we did so far, we took Matthew Liska's math simulations, and they have called clump sinking in.
Yeah.
So a student of mine, like Kundu, he modeled the reflection of these structures. Overall, the polarization was a bit lower because it's like an irregular surface, but it wasn't qualitatively different. It wasn't much different, other than being a little bit lower polarized and the line shape. I don't really remember if we had final results for that.
Okay, maybe one more question, then we should go for cookies. Also, there is the physics colloquium today, so I'm afraid I'm going to go to that myself. But, any more questions? Well, thank you again.
Yeah, thanks so much. for all the good questions. It's awesome.
Henrik is here for not only today, but
Just Friday and Monday a bit.
Friday and Monday. So yeah, maybe people who want to talk more should email me. Or if you cannot find his email, just email me.
And I tried to come maybe an hour before this meeting, maybe at the 2 o'clock meeting.
Yeah.
Or
Yeah.
before or after, and the same on Monday.
The seminar Monday is at 3.
At 3, then I come maybe at 3.
So there's a window between lunch and 3.
Okay, thanks.
Thank you. John White. Oh,